Recording in progress. Hi, students. In this lecture, first I am going to discuss Wheatstone Bridge. Let us see what is it. So it is now. It is a combination of resistors. Let us take. So connect a battery here. Suppose EMF is epsilon. EMF is epsilon. Suppose the C is A, B, C, and D. Across AB, resistance take it as R1. Across BC, resistance R2. Between AD means I can show like this resistance. It is taking as resistance R1, resistance R3, and here resistance R4, and this is R2. So here we are keeping one device which measures current, that is we are calling as galvanometer. It measures means whether current is flowing or not. By seeing deflection in that, we can say if there is any deflection, we can see there in that galvanometer there will be one pointer. If pointer deflects either left or right, that indicates flow of current. If pointer is not deflected, simply pointing like this only towards zero, then that indicates that there is no flow of current. This is known as galvanometer. Now here, when current flows, suppose current is I. After reaching the junction A, current divides into two parts. Let us take this is current I1 and this is current I3. Okay. Now here what we are saying that this is what we call Wheatstone bridge. This is known as Wheatstone bridge. Now in this, if there is no current flow from B to D or from D to B, then we say that bridge is balanced. I am repeating, if there is no current from B to D or from D to B, that means there is no deflection in the galvanometer. Okay, so no flow of current, then bridge is said to be balanced. So no current from B to D or D to B. Its meaning is that potential at B should be equal to potential at D. So when there is no potential difference, there is no current. That is simple logic. Now focus carefully. If you consider the potential drop across AB, that is I1 R1, potential drop across AB I1 R1, if it is equal to potential drop across AD, that is I3 R3, right? If this condition is satisfied, then potential at B will be equal to potential at D. Okay, I am repeating. We are taking condition that I1 R1 is equal to Y3 R3. Okay, So what it means? It means potential at B equal to potential at D. Okay. Suppose I'm taking at A, potential is now, so take it as 10 volt. Just let us say at A, potential is 10 volt, VA. Okay. Now I1 R1 equal to I2 R2. Suppose this value, take it as 1 volt. Okay, 1 volt. Now what happens is at B, potential will be, at B, potential will be. So we are knowing that when we are moving along the current flow, potential decreases. Now I am taking that. Let us take I1 R1 equal to I2 R3, that is equal to 1 volt. That means at B, potential will be 9 volt because 10 minus 1, potential decreases by I1 R1. I am repeating, potential decreases by I1 R1 when we are moving from A to B. That means it becomes now 9. And we have taken I3 R3 also 1 volt. That means when we are moving from A to D, potential decreases by 1 volt. So this is 10 volt means decreasing by 1. This is 9. And here also decreasing by 1. This is 9. Okay. So both have same potential. Right? That means no current flow. Okay. No current flow from B to D. That means this I1 flows now B to C. No current flowing from B to D means this I1 has to flow from B to C. Okay. Means in this also current is now same. Right. That means coming to here, if I3 current flows, in this also same current flows. Okay. Suppose I am taking here, potential is now take it as 0. The values are completely our choice. Just our convenience, I am taking values here to make it more simple to understand. And according to these values, see what we got. At B, potential 9. At D, also potential 9. Okay. Now, current is I1. This is current is I3. Right. You can see here potential is now 0. 0, this is 9. Difference equal to 9. And here 9, this is 0. Difference equal to 9. That means I can get one more condition from here. That is I1 R2 should be equal to I3 R4. I hope you got clarity from this to right. I1 R1 equal to I3 R3. Okay, that indicates VB equal to VD. Okay, then we get one more condition. This I1 has to flow from B to C. I3 has to flow from D to C. Then one more condition. Now see, take ratio here. I1 gets cancelled. I3 gets cancelled. Remaining is now R1 by R2 equal to R3 by R4. This is a condition for bridge to be balanced. Okay. So we say that, see carefully, R1 by R2 equal to R3 by R4. Or you can write R1 by R3 equal to R2 by R4. See carefully here. R1 by R3 equal to R2 by R4. Okay. So either we can take ratio for these two equal to ratio for these two. Otherwise, ratio of these two equal to ratio of these two. So both are same. Okay. So when this condition is satisfied, then we say bridge is balanced. And here one more point is that when bridge is balanced, if we interchange galvanometer and battery, that means battery is now in between BD and galvanometer is in between AC. Then also condition remains same once the bridge is balanced. Okay. Let us now focus problems basing on this. This is a question asked in 2001 for 2 marks. See question given. In the given circuit, it is observed that the current is independent of the value of resistance 6. Independent of the value of the resistance 6. Then resistance R6. Then the resistance value must satisfy. Okay. So remember, whenever having 4 or sorry, it is 5 or more than 5 resistors, there may be a chance of bridge. You can see 1, 2, 3, 4, 5. Having here 5 resistors. So there may be a chance of a bridge. Okay. Now see carefully. Here condition is given that independent of the value of resistance R6. Okay. Means even though this value is not there, we should get a same answer. Okay. Means same current. So the only possibility is that R1 by R2 equal to R3 by R6 or R1 by R3 equal to R2 by R6. Okay, directly we can say that. Then see what happens now. Coming to conditions, we can see option C, R1 by R2. R1 by R2. R1 by R2 equal to R3 by R4. Condition that R1 by R2 equal to R3 by R4. Or I can say R1 by R3. R1 by R3 equal to R2 by R4. R2 by R4. So condition C, right? Option C means bridge is balanced. When bridge is balanced, there is no flow of current through this resistor. When there is no flow of current, we can remove that resistance. No flow of current means we can remove that resistance. Means even the resistance is there, whatever may be the value, that has no effect on the value of current. Okay. Right. Let us see one more question. See what is given. A battery of internal resistance of 4 ohm is connected to the network of resistances as shown in order that the maximum power can be delivered to the network. The value of capital in ohm should be. So condition is given battery. It has resistance of 4 ohm. Okay. Connected to a network of resistances. Condition is it has to deliver maximum power to the network. Okay. For this network, battery has to provide maximum power. So for that, what should be the value of R? Okay. So before solving this, I will explain one simple problem to solve this question. See once. Let us consider one simple question, that is, take a resistance it is connected to one battery which has internal resistance small r. Battery EMF epsilon, it has resistance, it is internal resistance is small r, and this is now capital R. So condition is now relation between small r and capital R, so that this battery provides maximum power to the circuit. Okay, power should be maximum. For that, we have to get relation between these two R's. Okay. So first focus how to get power, right? So first I'm calculating here current. Current equal to epsilon upon R plus R, right? That is the current in the circuit. Now calculate power across the resistor. Power equal to I square into R. So these points we have discussed earlier, right? So I square epsilon upon R plus R whole square into R. Okay. Now condition is this power should be maximum. Okay. Then what we are doing is since capital R is variable, we have to differentiate that and make it equal to 0. Okay. Then we get for what value of capital R, power delivered is maximum. See derivative. So here epsilon is a constant. So focus on remaining part. Okay. R by square of R plus R. It is of the form U by V, right? Derivative. V du. V value R plus R whole square. V du. Derivative of R. It is 1. V du minus U dV. Derivative of R plus R whole square. It will be 2 into R plus R. Okay. By V square equal to 0. Okay. So that will be 0 if numerator is 0, right? So I'm making here a numerator is 0. So here we can cancel R plus R. So R plus R is equal to 2 into R. That implies R equal to R. Therefore, this external load receives maximum power from the battery if its resistance equal to internal resistance of the battery. This is now conclusion which we are going to use now in our problem. Okay. Now see carefully. Coming to here, how we solve this one. So first focus, we have here number of resistances. And I told that whenever having 5 or more than 5 resistors, there is a possibility of bridge. See carefully how to identify that. See this resistance and this resistance. These two are in series combination. See carefully. This resistance and this resistance both are in series combination. So this is now 2R. Okay. This is R. This is 2R. Now come this side. This resistance and this resistance, these two are in series. So this value how much? 2R. Okay. Now see carefully. This is a 2R. 2R by 4R. It is 1 by 2. Come this side. This is now R. This is now 2R. R by 2R. 1 by 2. Okay. R by 2R. 1 by 2. 2R by 4R. 1 by 2. That means bridge is balanced. Therefore, we can remove now this resistor. Okay. So once we are removing this resistor, see what happens now. Current flows like this. After coming here divides. Current flows now like this. And remaining part flows now like this. That means R, R, R. These three are series combination because this is removed. Next, this current flows like this R, R, 4R, 6R. So 6R, this is 3R. These two are parallel. So 6R, 3R, both are parallel means effective value 2R. Okay. 6R, this is 3R. Both are parallel. Effective value 2R. If this 2R is equal to internal resistance of the battery, so 2R equal to 4. So R equal to 2. So like this directly we can get the answer. Okay. So bridge balanced. Now external resistance how much we got? 2R. So 2R equal to 4. So R is 2. Right. So it is very simple if we are able to identify that there is a bridge. Right. Let us see next one. In the circuit shown in the figure, the current through is asking through 3 ohm resistor and 4 ohm resistor. Okay, right. This is the question asked in 1998 for 2 marks. Let us see what happens if current starts from here. Current flows like this. After coming here, divides like this and like this. Current divides. Next, again after coming here, current divides, right? Now see carefully. This current flows through 2 ohm, 4 ohm, and 2 ohm. So current through these three resistors is same. So these three are now series combination. I hope you are getting it. 2 ohm, 4 ohm, and 2 ohm. These three are series. So effective value 2 plus 4 plus 2, it is 8. This 8 is now parallel to this 8. 8 and 8, it becomes 4. Okay. Again 2 plus 4 plus 4, it is again 8. 8 and 8, it becomes effective value 4. Okay. 3 plus 4 plus 2, 9. That means current equal to 1 ampere. How much current? Current is now 1 ampere. Okay. So that 1 ampere after coming here, what happens? This is 8. This entire value is 8. Since both are equal, current divides equally. So current divides. So 1, sorry, this is a half and this is half. Okay. Because we got current 1 ampere. This 1 ampere flows here. Again, this is 8 and this also 8. So since both are same, again current divides equally. So again, half of a half, it is 1 by 4. So 1/4 of ampere flows through this 4. Okay. And next, what else? Right. So only option is now option D. Okay. It is through 4 ohm, current is 1/4 of ampere. Right. See next one. The effective resistance between point P and Q of the electrical circuit shown in the figure is asked for 2 marks in 2002. Now here what we can do, you can observe here about PQ. About PQ means upper part of PQ, lower part of PQ. Okay. Or I can say like this. This is if this is x-axis. Okay. Na? Let us assume PQ is now x-axis. Above x-axis, below x-axis, circuit is symmetric. Yes, I'm saying the line PQ, above line PQ, below line PQ, circuit is same. That means what we can say that at this point and at this point, potential will be same. Okay, na? That means we can remove now this 2R and 2R. Or we can say one more thing like, since the circuit is symmetric about PQ, current in this 2R and in this 2R must be same. In these two current is same means this current directly flows like this, not passing through this one. In the same way, current in this and current in this must be same. If these two are same means this current flows directly in this way. This won't pass like this. That indicates that at this point potential, at this point potential, they are same. That means we can remove this resistor and we can remove this also. Then 2R 2R series, that is 4R. 2R 2R. Again these two series, total value 4R. This is 4R, this is 2R, and this is 4R parallel. So 4R, 4R parallel means it is 2R. 2R and 2R parallel. That means option is, it is A. Okay. So directly we can say like this, most of the circuits Let us see next one. Find the EMF V and internal resistance R of a single battery which is equivalent to a parallel combination of two batteries of EMFs V1, V2 and internal resistance R1 and R2 respectively with the polarities as shown. This is the question asked in 1997 for 5 marks. So we have to find EMF for this combination and internal resistance for the combination, right? Means replacing by single battery. See how to solve. So what we are doing here now, first of all, draw the circuit. So it is given that a battery resistance R2, resistance R2, EMF V2, and next one resistance R1 and EMF V1, R1, V1. Condition is given that this is a plus and this is a minus A and B. So we have to find across AB what is the potential difference. We have to find VA minus VB. That value how much? Okay. Now see what we can do here. We can use now Kirchhoff's second law to find the current in the circuit. Now current flows. We can say like this. All right. It is now current flowing is now clockwise. Let us start from this point. Suppose the current is I. Okay. Then see what we are doing. Applying Kirchhoff's second law. We are moving along the current flow. Along the current flow, there is a potential drop. So I into R2 minus. We are moving from low potential to high potential. So writing plus V2. Next we are moving again low potential to high potential. Right, plus V1. Again we are moving along the current flow. Potential drop minus psi R1 equal to 0. That implies current equal to V1 plus V2 by R1 plus R. In fact, by seeing circuit only we can say directly, but just to have a clarity, I am writing equation once again. Okay, right. Now what we have to calculate? We have to get VA minus VB. So I am taking once again Kirchhoff's second law from A to B. Either you can take like this path, okay, or you can take a path like this. Okay, it is our choice because of finally we get answer same. Let us see. We want to get VA minus VB. I am taking from A. At A, potential is VA. Let us take potential is VA. Now I am taking path like this. We are moving along the current flow. Along the current flow means it is a potential drop minus IR2. Next, we are moving low potential to high potential. So plus V2. That is equal to potential at B. I am repeating. We are starting from A and reaching point B. Assume at this point potential VA. So VA. We are moving along the current flow. So it is minus IR2, low potential to high potential. So plus V2, that is equal to VB. Now from this, see what we get, VA minus VB. VA minus VB is equal to VA minus VB equal to, it is IR2 minus V2. Okay. Now substitute values in that. I value V1 plus V2 by R1 plus R2 into R2 minus V2 minus V2. See calculation part. So here what we can do is, it is I into R2, right? We got the value. See here what we can do. Calculation part. V2 R2. Okay, now that is minus. In this V2 R2 plus gets cancelled. Remaining is V1 R2 VA minus VB equal to V1 R2 V1 R2. Next one minus V2 R1 minus V2 R1 upon R1 plus R. So this is a potential difference across A and B. So if you want to replace these two batteries with a single battery, for that battery, this must be EMF. Okay, let us call it as V. Okay, na? And here, since you are given A positive, this is a positive, condition is that V1 R2 should be greater than V2 R1. Then this will be positive, this will be negative. Okay. Next, we have to find resistance for this battery. So since it is now combination of, it is a parallel combination of two batteries, parallel combination. In parallel combination, effective resistance equal to 1 by R1 plus 1 by R2. That means R value, it is R1 R2 upon R1 plus R. Okay, because it is given that it is equivalent to parallel combination of two batteries, parallel combination. That's why resistance is 1 by R equal to 1 by R1 plus 1 by R, right? So directly by seeing this, we can get a correct, just finding potential difference, right? So this is the answer, EMF for that battery. This is our resistance of that battery, right?